So we are nearing the end of the course now, the course on electronic testing. So far we have looked at digital testing, memory testing, analog testing. Um, Now we'll look at some recent developments in the area of testing and what are some of the challenges that people are facing. So let us. So we have talked about quality, right? So I mentioned to you that there is something called as DPPM, right? So DPPM or defective parts per million. But when chips are now used in automotive and industrial electronics, biomedical electronics, etc., the expectation will be that they will have zero defects. Okay, very difficult to do this, right? People are now reducing the DPPM to DPPB, that is defective parts per billion. So there is a great demand for very high quality products, and there are many quality standards, and we'll talk about these, right? So there are many quality standards. The second aspect is reliability. So even this we have mentioned. See, in the early days, the electronics was mainly used in things like calculators, computers, later mobile phones came up. In these applications, typically people change their calculator maybe once in a few years. Computers also, we all change our computers once in maybe 4 5 years. PCs, mobile phones, people may change even uh, in a shorter duration, maybe 3 4 years. But what about things like industrial robots, right? Or biomedical electronics? See, there may be implanted electronics, etc. So we can't, sort of change these things at will, right? Even in automotive, right? The life expectation of a electronic component in a application like automotive can be anywhere from 10 to 15 years. But at the same time, we have also seen that there is a lot of aging that happens, and there are many phenomena which result in failures. We have talked about electromigration, I believe. We have perhaps talked about you know gate oxide breakdown. We have talked about maybe charges getting trapped in the gate oxide, and VT, or the threshold voltage, sort of tends to become higher, right, over a period of time. So these are all aging effects, and as a result of this aging, two things can occur. One is the electronics become slower. Remember, that the speed of a transistor depends on Vt. So, if the transistor experiences an increase in Vt, then it will become slower to switch. So, people have observed phenomena where the transistors become slower over a period of time. There may also be, defects such as opens, shorts that can develop over time. For example, electromigration, it can result in a open circuit over a period of time. It can also cause short circuit over a period of time. So, reliability has become an important consideration in these applications where the life expectation has to be very high. So, what does it mean? Either we produce electronics which has a lifetime of 10 or 15 years, or we add what are called as aging monitors. So, the chip will monitor its own age, and when it reaches an age which is you know unacceptable, right, meaning the defects have not yet appeared but they are likely to appear. When such an age appears, then the warning can be given. It's just like built-in self-test, right? So age monitors can be built into the chip, and the user can be told that you must now consider replacing this part, otherwise you are likely to face some difficulties. Okay. Similarly, security, right? We talk about chip security in a number of different situations. For example, there are companies that may be engaged in producing counterfeits. Meaning, from a outside viewpoint of from the outside, these chips look exactly like that of a good company, well-known company. It will have the logo, it will have the same look and feel, but inside is a counterfeit. Somebody else has designed that chip. It will be compatible to this chip. It may be available at a shorter price, at a lower price. So customers may be tempted to buy from that source. Okay, so there is the original part being sold on some portal. So the company is selling the parts through its electronic portal, but somebody else is selling similar parts. Okay, it appears that it is the same company but available at a lower price. What is the catch? The catch is that these guys may not have done all the testing, etc. Okay, it may be poorer quality. It may have poor reliability. So if somebody buys this counterfeit chip and if it fails, then unfortunately they will blame this company. They will come to them and say, these parts have failed. Then the company has to unfortunately verify whether they made the chip, and they had to prove to this vendor, to the customer, that they did not make this chip, somebody else did. The other thing that could happen is, somebody went through waste electronics or e-waste. See, the waste that we throw away, electronic waste, like old phones, they will be, they reach a center where somebody may be extracting these ICs, right? And they may recycle them into the market. Unfortunately, these ICs, they have already been used for many years, and as a result, if their lifetime was, let us say, 10 years or 5 years, maybe already they are near the end of their life. So if you purchase such fake, not fake, such old ICs from some second source, right, you are likely to face reliability issues. Okay, so this is also a big problem. So you must make it possible to trace the die. So each die will have what is called as a die ID, a number which is unique to that particular ID. Using that, it should be possible for you to tell whether you made this die. When did you make it? Was it 10 years ago, 5 years ago? So companies will store all this data about all the chips that they are making, etc. The cost of testing is also a big consideration. Okay, I have mentioned to you that there are three types of costs, right? There is a design cost, there is a manufacturing cost, and there is a test cost. In this class, we are mainly interested in the test cost. So, as the complexity of the SOCs increases, we have to have lot of different tests, right? I have told you about single stucket fault. I have told you about transition delay fault. I have told you about bridge faults. So, with more fault models, you will have more test patterns, and that means test application time is going to be high, and that means test cost will be high. So, people are trying to address the cost issue, right, by looking at things like multi-site testing. Meaning, don't test one chip at a time, but test multiple chips at a time. The second angle that they are pursuing is, can we reduce some of these things like burn-in test? These are very expensive to run. They require specialized equipment like ovens. Okay, so burn-in tests, they cost a lot of money. So if we can avoid those, that will help. So what are the ways to reduce burn-in test? So we use the word test engineering these days. Okay, so companies recruit different kinds of engineers, design verification engineers, design verification engineers, they recruit people who are into digital design per se, analog design, then physical design. In addition to that, they recruit quite a few design for test engineers who take care of adding scan chains, logic based, generating the fault coverage numbers, analog test, memory test, all that is their responsibility. Test engineering is somewhat different. Okay. So test engineering is mainly about, they're actually applying tests. DFT is more of designing the chip for test. But test engineering means the test engineer is responsible for validation testing, okay, maybe test optimization, okay, working with ATEs and developing test programs. Okay, all this is they may also do PCB design for test boards. So if you are going to validate a chip, you may have to design a simple PCB where you can plug in your IC. A very simple system may have to be designed. So that is the test hardware design. Then you have to learn how to use the ATE. You have to learn how to make those measurements. You have to learn how to optimize the test program. And when defects are found, when faults are found, you have to go back and find out what the defect is and perform some failure analysis. So these are all the activities of the test engineer. And that person must be familiar with a number of different kinds of tests like logic based, memory based, analog based. Then things like cell aware testing, low power testing, adaptive testing. So all these are also part of the test engineers. It doesn't mean that every test engineer will have to do all of these. But what I am trying to impress upon you is that this is how they are, different from other engineers. So they are knowledgeable in these areas. Okay. So again, same thing, right? You have to know about testing of analog components, power ICs. Then there are memory based architecture. You should know about D-based and such compression, right? We talked about how to use test compression. So all these are their knowledge base. Then more recently, there is a lot of emphasis on bringing artificial intelligence and machine learning into test engineering. Then there is also, we talked about quality, how to improve quality, how to improve reliability, and how to improve security. Okay. So presently, we don't discuss all these things in an undergraduate class. Okay. I think that way you are all lucky that you are getting this kind of exposure, right? Test engineering is a very, in India, it is, I would say, in the past few years, test engineering has arrived. Right. Earlier, test engineers were there in places where the fab was located. Okay. So if the fab is here, test engineers used to be residing close to the fab. But now in many countries there are test services being provided. Just like once upon a time, design service was a big buzzword, right? What is a design service? See, there may be a big company which manufactures designs and manufactures chips. They outsource some of their work to design services. So this guy is a big company, he's a giant, but they are willing to give some of their work to these design services companies. In the same way, they are now looking at test services companies to help them in some of these activities. Maybe they are helping them in using a particular ATE, developing optimized tests for a particular ATE. So test engineering is definitely a good career option. So if you are a kind of a person who likes to work in labs and develop test programs to program these ATEs, etc., then test engineering is something that you can consider as a option. There is still a lot of software development as part of test engineering. So you will have to know how to use C++ to write test programs. And I think from a satisfaction point of view, so you are very close to the end of line. Okay. So that way you may find the job very satisfying, that whatever you do directly impacts the company. Whereas in design services, I'm not saying that is not important, but I'm saying they will not see their efforts bearing fruit right away. A design may take many years. So what the design service engineer did, or what the designer did, they will see the effect of that many years later. Okay. But in the case of test engineer, they will see the effect right away. Okay. So that is the advantage. So we have seen this background already. Okay. See, today the technologies that are considered cutting edge technologies are things like 7 nanometer, 5 nanometer, and I have even heard about 3 nanometer, etc. Okay. So these are called as cutting edge. But you should not think that these are the only things that exist. We still have 22 nanometer, we still have 45 nanometer, we still have 65 nanometer, we even have 90 nanometer fabs. Okay, all of these do exist. These are meant for customers who are trying to do aggressive scaling, right? But not all applications require that kind of cutting edge technology, right? So the scaling has sort of slowed down, right? And as a result, people have started focusing on what can we do at the system level. So that is how these chiplets, remember we talked about chiplets earlier. So it's a system level optimization. It is a packaging level optimization. So the innovations are happening in these areas like packaging, so that we can still have an impact on cost, etc., without having to move to these aggressive technologies. So in the early days, people used to talk about design productivity gap. This term was used in the 1990s. What does it mean? See, the technology may allow you to make a chip of about, let us say, 10 million transistors. But because it takes us a lot of effort to sort of design these chips, right? So imagine that a project takes about 5 years, and at the end you are able to put about 8 million transistors. The chip has 8 million transistors and it took 5 years. So you can calculate how many transistors that designers put in a particular day. Okay. So 8 times 10 to the power 6 divided by 5 times 365. This is the number of transistors that you can put in a particular day. So if your technology allows you to make 10 million transistors, 20 million transistors, etc., technology is giving you that option. Okay. But our productivity is still very low. So for us to reach this level, at this rate, okay, it may take a long time. Our design productivity, it takes many years for us to reach that level. But because people don't want to wait that long, okay, many times they don't have the ability to optimize the design, etc. So the productivity gap means the technology allows you to put 8 million transistors, and you are taking a very long time to do such a design. So you will possibly not put 8 million transistors. You will only put a lesser number of transistors, and you may still rely on system on a board. Okay. So suppose you don't want to design such a big chip because it is a lot of effort, right? So you may design two chips, each have 4 million, and you may take about 2.5 years to do that. Then you will integrate at the package level. So unfortunately, that resulted in more area, etc. So that is what is called as design productivity gap. So now people talk about test productivity gap in the same way. If we become more knowledgeable in the area of testing, then we can develop more efficient tests. We can learn how to use the ATs in a more efficient way, and that will reduce our test cost. Okay. So that is a productivity gap. And increasingly people use IPs, okay, intellectual property. So today it is not that they design everything from scratch. They design mostly at the top level by reusing blocks. So we may have used a ARM microprocessor. Similarly, we may buy memory from maybe ARM or other company. Okay. Then controllers may also come from other companies. So the job of the IC designer is more of IP integration. Right. So when such is the case, the role of test engineer and DFT engineer becomes more challenging because they have to understand how to use that IP, what are the test, how these scan chains have been inserted, okay, what test modes are available in that IP. So they have to understand all those behind the scenes. Okay, and as a result, I would say verification, test, and validation are perhaps more challenging now than design itself. Okay, so I think this part we have already discussed, so I'm not going to talk about it again. So this is something that happens in the early days of the product development, where you are verifying the design. You still have not gone to hardware, you still don't have any chips yet. Whereas when the chips come back, you perform validation just to see whether the product looks promising. Will it make money in the market? Will customers accept it? Does it give the right system performance? And if the validation engineers are happy with that product, then we are willing to go and do mass production. And at that time, we have to do testing in a efficient way.